Welcome to Pomodoro Joe for Saturday, June 17th, 2023. Today we're doing LeetCode problem 1187, make array strictly increasing. This is a hard problem. Given two integer arrays, array 1 and array 2, return the minimum number of operations, possibly 0, needed to make array 1 strictly increasing. In one operation, you can choose two indices, 0 less than or equal to I, which is less than array 1 length, and 0 is less than or equal to j, which is less than array 2 length, and do the assignment. Array 1 index I is equal to array 2 index j. If there is no way to make array 1 strictly increasing, return -1. Okay, so what this is saying is we have two arrays. Array 1, which is the one we are trying to make strictly increasing, and array 2, which is a set of elements that we can essentially swap into array 1. Okay. So let's take a look at this. In this first example, we have 1, 5, that is increasing, so we're all right. But then we go to 3, that is decreasing. So at this point, we need to make a change. We can either swap out 5 for something that's smaller, or we can swap out 3 for something that is greater. Now, if we swap out 5, whatever we swap it out with has to be less than 3. And if we swap out 3, whatever we swap out, it has to be greater than 5. Or I guess there's the possibility where we swap both 5 and 3. So we can swap out 5 for something that is less than whatever we swap out 3 for. But that gets really complicated. That's like too many things moving at this time. All right, so what they're doing is they're going to swap out, it looks like just 1. So they'll swap out 2 for 5. So you get 1, 2, 3, 6, 7, and that's strictly increasing. Now in example 2, they start out the same, 1, 3, 5, 6, 7, but our array 2 actually has fewer options. So at this point, we can't just swap out 5 for 2 because we don't have that option. And we can't swap out 3 for something greater than 5 because we don't have that option. So we actually have to swap out both. So we have to swap out 5 for something that's greater than 1, so that's either 3 or 4. In this case, it would be 3, because then we have to swap out 3 for something that is greater than 3, which is 4. So we have two operations. And then finally, we have this example where you can't do it and you have to return -1. Okay, so I think for this, I need to narrow down our options. This is a little bit too complicated. There's like too many things moving here. So let's see what we can do. When I run into a situation like this, sometimes it helps to take a look at the extremes. Now, if I look at the very beginning, we're constantly increasing. We have to look forward. There are a lot of different elements to look forward to try to figure out how do we change these options, how do we change our values. But if I start at the other end, if I start out here at 7, all right, this narrows things down. This might help. So let's start at the end. We start at 7. Now 7 will be the largest element in our array when we're done. So our options here are we keep this 7, or we could swap this 7 out for something else. Now, if we swap this 7 out for something else, we definitely want to swap it for something larger than 7. If we're paying the cost to swap out an element, especially because we know that this is the largest element in our array, we don't want to swap it out for something that's smaller. So let's see. In this case, we don't need to swap it out at all. There is nothing that is larger, so we keep our 7. All right, so that helps. So we keep the 7, we don't do anything. But we do have the two options. If we did have something in here that was larger, we might want to swap it out. So at this point, we have two options. Keep the 7 or swap it for something larger. Okay, now we can do a recursive call. So this actually starts to break things down. We've eliminated this element. We've taken care of it. We don't need to worry about it. Let's move on to the next element. So that's going to be moving down to element 6. Okay, so at this point, we have the same sort of algorithm. We can either keep the 6 or we can swap it out for something that's larger than 6. Now, at this point, I guess it's a little bit complicated because we only want to swap it out for something larger than 6 if that is less than the next value. So we're going to have to keep track of what is our next value so that we don't accidentally swap it out for something that's larger than our next value. And we keep moving down the line until we get to the end. So I think that's how I'm going to approach this problem. I'm going to start from the end and work my way backward to the beginning and swapping things out for larger elements if we need to. Okay. So with that, we'll put 25 minutes on the Pomodoro timer and we will get started. All right, in here, I am going to want a recursive function. So we'll define our make array increasing and recurse. Let me just grab this. And what are the pieces that I need? Let's see, I need to know what index I'm on because I'm working my way from the end to the beginning. So we'll keep some index into array 1. And I need to know, okay, so when I do my swapping, I'll be swapping out for something in array 2. So in this very first swap, I'm going to try to find the largest possible value in array 2 to swap out for this element. Now, in my recursive call, I'll be doing the same thing. I'll be looking for the largest possible value in array 2 to swap out for this element. But I don't necessarily want the entire array 2, for one, because we've already possibly used one of those elements. And 2, if I'm looking for the largest element every single time through the loop, it doesn't make sense to search array 2 over and over and over again looking for large elements. It would make more sense to sort array 2, then keep track of where we are in array 2, so that we can just keep moving down in array 2 just as we're moving down in array 1. So let's sort our array 2 here. Okay, so I think at this point I might want to keep track of where I am in my sorted array 2. So I'll have another index, I2. That tells me what's still available for me to use out of my sorted array 2. Let's see, what else will we need? Well, we'll need to know how many operations we've done, so we'll keep track of some count of the operations that we've performed. We'll also need to know what our maximum element is, or our next element in our array will be. Now, I'm not actually going to modify my array 1, so I'll just keep track here of what that next element is. So I'll call it next value. So that way, when we move from 7 to 6, I can check to see if my value that I'm replacing here is less than the next value without actually having to change anything in my array. Okay, so I'm keeping track of my current index. This will be going from the length of array 1 down to 0. Then I'll be keeping track of how many elements I still have left in my array 2 that I can use. So this will be the max element also starting at the end of array 2, working our way back down to 0. We'll keep track of the next element so that we can make sure that we're not essentially going above our next element every time we swap out. And then we'll keep track of how many different operations we've performed. Okay, so base case first. What's our base case? Well, that's when we've reached the end. So if our I1, so this is our index into our array 1, if that's less than 0, then we're done. And we can return count. That's how many operations it took us to get to this last index. Okay. What else do we do? Well, let's grab our value. Let's make sure that we know what we're dealing with here. So this is going to be our array 1 at this index, I1. Okay. Now at this point, we have two options. Option 1, we will keep this element, we won't do anything. Okay, so that's pretty easy. So option 1 will be we keep this element, we don't do anything else. So that will be a recursive call then. Let's see here, we can make increasing recurse. That's how many operations will it take if we keep this element, but we can move on to the next element in our list. So I minus 1, and we haven't done anything with our second array, so we can keep that element. Now this value, we're calling it the next value, so that's going to be this current value. So when we go to our next value down in the list, we can look back up the chain to find this value. And then our count doesn't change because we haven't done any operations. Okay, so that one's pretty easy. All right, let's do that. Now one thing I didn't check is if this value is already less than our next value. Because if it's not, then we can't keep this value. It's not actually valid. So I might need to do that here. Okay, so if this value is less than our next value, well, then we're allowed to do this op. Otherwise, we're not allowed to do this. So let's keep our op1 out here, and we can set it to, kind of tempted to set it to -1, but I'll be comparing, looking for minimum values between option 1 and option 2. So I'll set this to infinite to start with. Let's just say this is takes the most amount of operations possible. All right, then we have option 2. So option 2, in the previous option, we kept the element. Now for option 2, we're going to replace the element. And that's going to be replaced with the largest element that we can find in our array 2. Largest remaining element, I should say. And again, we'll have some default value. It's going to be infinitely large, just so when we do our comparison later, we can have a minimum comparison. Okay, so at this point, we are going to be swapping out our element for some other larger element, but we don't know what that larger element is yet. We have to find it. So let's find our new index 2 here. So we'll start it as I2. Now we're trying to find the largest element in our sorted array 2 that is less than our current max, which is this next value. Okay, so we can keep going from I2 down. So let's see, while the new index, so we're finding some new index that we'll be passing down, or maybe I'll call this element index. I'll do that. Or swap index. I'll call it swap index, yeah. So we are swapping this element and the swap index, which is the index into our sorted array 2 here. So while our swap index, let's see, while that is greater than 0, and while the element at the swap index, so this will be our sorted array 2 at swap index, if that is greater than or equal to our next value, so that's the next value in our list here, we need to find something that's smaller than this. So we'll keep moving this swap index down. So we're just looking for something in array 2, starting at essentially our current max value, and we'll be moving down our array 2, finding smaller and smaller values until we find something that's still in array 2 that's smaller than our next value, and then that's something that we could swap out for. If we don't find one, then we might not be able to do this swap. So now we do have to check, did we find one? So if our sorted array here, we'll have to grab this guy. So if we found an element that is indeed less than this next value, well then we can do the swap. Why did you do that? There we go. And now we can do op2. So that's going to be our recursive call here. Just grab this here. We still go down 1 in our array, but now we have a new swap index here. So we have to do swap index. We can actually do, I think, swap index -1 because we've actually used up this index. Now our value will be, actually that'll be this new value here. So maybe I'll call a new value. That's going to be the value that we're swapping in. And because we performed an operation, our count will be increased by 1. Wow. Okay, now at the end, we've done our 2 possible options. We've either kept our value the same, or we've swapped our value out for something else from our array 2. Make sure I'm using sorted array. Yes. Now, what do we return? At this point, we return the smaller of the 2, or -1 if we don't have one that's smaller than the other. We'll turn option 1 if option 1 is less than option 2. Now remember, these are default to infinite, so if they're both infinite, they won't be less than. Otherwise, we'll return option 2. And now, outside of this whole thing, we'll have to check to see if our value is infinite, if our result from this is infinite, and then we'll return -1 if it happens to be infinite. Okay, so I think this covers our recursive function. Next up, we need to actually call our recursive function for the first time. So our result out here will be equal to this function. And what do we pass in? Well, we need to pass in our length, basically array 1 minus 1. That's our max index for our start, because we're starting at the very end. And let's see, we need to get the length of array 2. Actually, I'm going to use sorted array 2. At this point, they're the same, but I think we're going to probably make some changes there. And again, minus 1. Now let's see, our next value. We don't have any next value when we start. We're at the very end of our array. So we'll just set that one to infinite to start with. We're just looking for things that are less than the next element. So infinite's a pretty safe bet here. And then number of operations will be 0. At the end, we will return our result. But again, I might be returning infinite here. So we return result if result is not infinite. Else we'll return -1. It's a little bit ugly, but I think it should handle our problem. Okay, so we have our recursive function. We're going through. When we reach the end, our base case will return our count. Otherwise, we will have two options. We either don't replace the value at all. If we can, we do have to make sure that our value is less than the next value. Otherwise, we do have to replace it. If we don't have to replace it, we'll just move down our list. If we do have to replace it, or if we want to replace it, we find our replacement value if we can. If we do have a replacement value, we'll replace it, and then we will make a recursive call incrementing our count. Okay, let's see if this works. Okay, that seems to work. Now I'm pretty sure this will not run in the time that we need it to, but there are some things that we can do to speed this up. Let's submit this first and just see if we can get it to pass. Okay, time limit exceeded, and you can see from this test case, that's a long one. Although we do all right, we beat 19 out of 21 test cases, so we just need to improve this a little bit. So we'll grab this. Okay, so the first thing that we can do, very simply, we can use dynamic programming to essentially keep track of if this were a key and we've already calculated this entire process one time, we can cache out the value. So we can use a key value store. For me, since this is a hard problem, I'm just going to do the easy way, and we're going to use caching for this. Now, caching will do exactly what I described. It will essentially use these arguments as a key. Anytime it sees the same set of arguments, it will return the same value. So it will run this process one time, the first time it sees this set of arguments. Anytime after that we call the same function with the same set of arguments, it'll just return the cached value. So that should save us some time. However, we've got a lot of values here. The more values you have, the more permutations you have on this signature, which means that you are pretty much going to have more misses, more cache misses. You aren't going to be able to maximize your caching. So we might want to find a way to reduce the number of values here. And I can already see one, this count. Instead of keeping track of the count and passing it down, we could return the count and basically do a bottom up and return our value at the end. So at this point, let's just try the caching, see if it can get us past this one test case. If it can, then we can move on. If we can't, we need to address this. Okay, we still get a time limit exceeded. So let's see if we can address this problem. So let's see if we can remove this count. We don't need to keep track of the count and pass it down. We could return our value. Well, how do I put this? This is sort of a different style of recursion. There's tail recursion. In this case, we will, instead of pass our count down to the end and return the count, we'll actually keep track of the count, put it on the stack, and push it up to our result. Okay, that doesn't make a ton of sense. Let me just show you. So instead of passing this count, we can just ignore that count. Now here, we're just passing 0 down all that way. We can say, instead of passing 0, we just return this option. Now here, instead of passing this count here, we can just return 1 plus however many operations it takes to get here. Now at this point, we have to change our base case to return 0. It doesn't take any additional operations once we've gotten to this case. So this will return 0, pop up to here. This will have a 0, this option will just be 0. This option will be 1 plus whatever the return value was from these recursive calls. So this should get us a little bit of the way. This caching might be a little bit more efficient. Looks like I got something wrong. Oh, I need to change some of my arguments, like this guy. I think I changed the others. Yeah. So this might not be enough to, oh, it is enough. So that was enough to get us to pass this test case. Now, it doesn't mean we'll pass all the test cases, but we got 19 out of 21, so this might actually be enough. And that was enough to get us to pass. All right, so we are passing, and we only beat 5% for runtime and 6% for memory, so we don't do great. There are definitely ways to improve upon this particular algorithm. Now, one thing we could do, we're also keeping track of, let's see, our index into each of the arrays and our next value. I don't think we can ignore the index into the first array because we're moving from the top or the end down to the beginning. And I don't think we can get rid of the next value. But this value, this just keeps track of where are we in our sorted array 2. Well, right now I'm not doing a very efficient job of figuring out where our next value will be or what the next best value to swap out will be. At this point, we're just keeping track of where are we in this sorted array, and we're doing a linear search backwards to find that next value that's less than, I guess, the maximum value that's less than the next value. So this linear search is not super efficient. One thing we could do is we can do a binary search for the same index point. So that might be what I would do next. Swap this out for a binary search. And once you swap that out for a binary search, you might actually be able to eliminate this index, which actually makes this caching more efficient. So that's like a double win. You win on the binary search because you're not doing a linear search through all your elements to find this index, and your caching becomes more efficient. Let's see, we have 7 minutes. Let's do it. All right, let's do it. So in here, let's make a new function. We'll just call it like find insert index, or what will we call this? Not insert. Let's call this find value index. And what do we need for this? Well, for now, let's just keep our exact same function for this. Let's just grab this while. Okay. So it looks like for this while loop, we need to know our swap index. And what else do we need to know? Our next value. Okay. So for this, we just need to know our starting index because the swap index is actually this guy here. Let's grab that. So we need to know our I2, and we need to know our next val. So we'll do this and we'll return our swap index. So this is a very simple swap, or this is a very simple replacement. So I can remove the code and replace it with this function. So this guy, pass an I2 and next val. Okay, so this should still work. We didn't really change anything. We're just making this a function call, which helps us refactor this a little bit easier. Okay, so that still works. Now let's see if we can replace this guy with something that's more efficient. Well, let's see. We still need to know our next value. We may or may not need to know this. So let's do a binary search. Okay, let's start. We'll have some low index. That's 0. We'll have some high index. And that will be the length. Oh, in this case, this will be our I2, actually. So we have a low index, we have a high index. Now we need to do our binary search. So while our low index is less than our high index, we'll find our midpoint, and our mid index will just be the low plus the difference between our high and our low divided by 2. So I'm going through this really fast. If you don't know binary search, check out some of my other videos or do a Google search. I'm not going to explain all the details here. This is a basic binary search. So we'll find the midpoint, the low plus our delta between the high and low divided by 2. And if our values, so now we have to check if our sorted array 2, because this is the array we're looking at this midpoint, let's see, if this is less than our next value, or if it's less than or equal to, no, if it's just less than. If it's less than our next value, we can increase our low, and that can be the mid plus 1. Otherwise, now we've got something that's higher than our next value. So we need to reduce our high value down to our midpoint. Now this one's a little bit tricky because once we've broken out of this, we have our low, but that low might be equal to our high value, and we're definitely looking for something that's lower than our high value. So we might need to do a little bit of an adjustment on our low here. So we can return our low if the sorted array 2 at this low is less than our high value or our next value. Otherwise, we'll need to return low minus 1. Okay, so let's get rid of this. That was our linear search. Now we've done a binary search. Let's just see if this still works. And that still works. So this actually should be a little bit faster just as is. Let's see if this is. Let's try that. And we have 2 minutes. All right, I think we can do this. Okay, so we're beating 7% now, so we're a tiny bit faster. 5% before, 7% now. So that binary search does save us a little bit. Now, let's ignore this I2. We can do a binary search on the entire sorted array 2. We don't actually have to keep track of this I2. So in this case, this will be the length of our sorted array. So we'll do a binary search on our entire sorted array. I just got to thinking, we might have duplicates in this sorted array. That might present issues. Well, let's try this. We'll go through the entire sorted array. So we don't need to keep track of our high value or our high index in our I2 here. So we can actually get rid of this altogether because we no longer need it for this, and this is the only place we were using it. Which means that we can get rid of this. We might run out of time here. If we run out of time, I'll just push through. And we don't need this. Okay, let's see if this still works. Okay, index out of range. Oh, because this has to go to length minus 1. That still works. Now this caching might be a little bit better because we're no longer looking at 3 variables for the input. We're just looking at 2. And we are out of time. Well, let's just go back and see how we did. A little bit better. We're at 10% for runtime, up from 7% before, and we're doing much better on memory, 15% on memory. All right, last thing. As I just mentioned, I realized this sorted array, this might have duplicates. And if we do have duplicates, we're going through a lot of extra effort. Let's see if we can remove those duplicates. So a simple way to remove duplicates is just to use a set. So I'll call this the array2 set, and that's just going to be a set from array2. So now we've got array2 set, and we can do this. We can just have our sorted array2 be the set sorted set. And I just realized we can even do a cache here. I'm changing too many things, but that's all right. I think this should work. Still works. Let's see if we can do any better. I bet this one does make some improvements. And we do a lot better. So now we're up to 62% for runtime and 15% for memory. So this is a big improvement over our initial algorithm, which did work, but only got 5% for runtime and 6% for memory. All right. There's still other things you can do in here to improve upon this. I am going to leave it here though, because we are out of time. So I hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.